Pluto is a distant and bewildering planet that was once part of our nearby planetary systems family. However, disturbing announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They suggest that this freezing world is on a potential brief trajectory with Neptune. But how could this happen, and what might be the results of such an enormous event? Are we witnessing an impending collision, or is there something different about this oncoming immense accident? Join us as we explore the potential consequences of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet partly because of its exceptional orbit, remains a subject of interest and study in the cosmic community, as demonstrated by recent forecasts by leading specialists. Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential hazardous effect between these two planets that could represent a tremendous risk to Earth. How is such an event even possible? Pluto's excursion around the Sun is unlike any other planet in our nearby planet group. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its extraordinarily bent shape, deviating significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, determined at 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to the other planets. This inclination and irregularity add layers of complexity to its orbital pattern. Possibly one of the most captivating parts of Pluto's orbit is its convergence with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we might expect from their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to sort out its strange orbit. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's path stood out with its steep inclination and irregular shape. The mystery grew with the realization that Pluto's orbit indeed crosses Neptune's. The complexity of Pluto's orbit amidst these intricacies is proof of the complexities of space mechanics. The three-body problem in space is about sorting out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. For Pluto's situation, this issue shows how its orbit, Neptune's path, and the Sun's gravity all work together in a complex way. The terms alpha libration, scope libration, and VZK swaying are important to this enigma. According to astrophysicists, what's keeping all planets in their orbits is a phenomenon called alpha libration with respect to Pluto and Neptune. This term essentially means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from impacting each other. Extension libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned well above their orbital plane, offering an additional layer of protection from potential impacts. Another significant factor in this situation is the VZK sway, named after three researchers, Zippel, Leo, and Kai, who studied how things move in space. It's about how three celestial objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. In Pluto's case, VZK helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming turbulent, this swaying helps keep it moving smoothly from now onward indefinitely. The VZK sway shows that even though things in space may appear wild and unpredictable, some patterns and rules keep everything together. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or lose its course. This three-body problem helps in understanding how these orbits change based on how these celestial objects pull on each other. Focusing on this helps us learn more about Pluto, our solar system, and distant stars and galaxies. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is still relatively chaotic, with minor variations in starting conditions leading to massive differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over exceptionally long timescales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where for every orbit Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's orbit stable. However, Neptune isn't the only one contributing. Jupiter's gravity also plays a major role in defending Pluto's orbit, and Saturn contributes significantly as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable orbit for a long time, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These phenomena are critical when it comes to the universe, as they maintain the order and consistency of celestial bodies' movements. Without these forces, the solar system as we know it would be a place of much greater disorder and unpredictability. Bodies like Pluto might collide with others or be ejected from their stable orbits, causing a domino effect on other celestial bodies. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the dynamics of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of stability through the intricate exchange of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this oddity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term trajectory. In the vastness of our solar system, Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its structure and behavior. One of the most intriguing aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and other compounds. The New Horizons mission, which flew by Pluto in July 2015, provided striking data about this distant world. The surface of Pluto is characterized by vast fields, towering mountains, and deep valleys. One of the most remarkable features is the Sputnik planitia, a colossal heart-shaped plain primarily composed of nitrogen ice. This area showcases a diverse array of landforms, including large ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its great distance from the Sun and low temperatures. Another captivating aspect of Pluto is its atmosphere, primarily made up of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin but shows intriguing seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply revolving around Charon. This unique relationship contributes to the complex gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, giving scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the development patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is the potential impact on our understanding of the solar system's evolution. Gravitational interactions from neighboring giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper belt. Such interactions can lead to shifts in orbits, possibly resulting in collisions or ejections from the solar system. As scientists continue to explore the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, sparking discussions about what it means to be a planet. In conclusion, Pluto's orbital relationship with Neptune and its position in the solar system serve as powerful reminders of the complexity of the universe. Through continued exploration, we can deepen our understanding of these faraway worlds and the forces that govern their motion. Continuing our exploration of Pluto's intriguing orbital dynamics, it's essential to recognize how the gravitational forces exerted by distant planets shape the behavior of objects in the outer solar system. While the orbit of Pluto may appear chaotic at first glance, it is precisely these intricate interactions that allow it to maintain stability despite the seeming disorder. As we dive deeper into the mechanics of Pluto's orbit, we uncover more layers of complexity, shedding light on the dynamic processes that govern the motion of celestial bodies. One fascinating aspect of Pluto's relationship with Neptune is the long-term stability of their orbits, despite their periodic proximity. This is due to a special resonance between the two bodies, known as a 3:2 orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance keeps Pluto and Neptune in a stable configuration, preventing them from colliding despite their orbits crossing. The stability provided by this resonance is an elegant example of how gravitational interactions can ensure the orderly movement of celestial objects. This 3:2 resonance is a result of the gravitational tug-of-war between Pluto and Neptune. Each time Pluto and Neptune approach one another in their orbits, their gravitational fields interact in a way that ensures their paths remain synchronized over long periods. The result is a system where even as Pluto crosses into Neptune's orbit, the two bodies are always carefully spaced apart by the stable resonance. As a result, the likelihood of an impact is virtually non-existent, despite the initial appearance of danger. Further study of the Kuiper belt, where Pluto resides, reveals that Pluto is not alone in this unique orbital relationship. Many other objects in the Kuiper belt also exhibit gravitational interactions with Neptune, resulting in similar orbital resonances. These objects are often referred to as Plutinos because their orbits are similarly locked into a 3:2 resonance with Neptune. This large group of icy bodies further underscores the importance of Neptune's gravitational influence in shaping the structure and stability of the outer solar system. In addition to gravitational resonances, the process of planetary migration likely played a key role in shaping Pluto's current orbit. Planetary migration refers to the slow movement of planets over millions of years caused by interactions with the protoplanetary disk or other bodies in the early solar system. During the formation of the solar system, giant planets like Jupiter, Saturn, and Neptune are believed to have undergone migration, shifting their positions and altering the orbits of smaller bodies in the process. This migration could have influenced Pluto's orbit, nudging it into its current eccentric and inclined path. The migration of Neptune in particular is thought to have played a pivotal role in the current configuration of the Kuiper belt. As Neptune moved outward from the Sun, it likely cleared space for other bodies, including Pluto, to take up residence in their current orbits. This dynamic process helped shape the distribution of icy bodies in the outer solar system, leaving behind the diverse array of objects we observe today. Another aspect of Pluto's orbit that deserves attention is its periodic crossing of the orbital path of other objects in the Kuiper belt. While the likelihood of a collision is extremely low due to the stability of the resonance with Neptune, the potential for gravitational interactions with other objects in the belt remains a possibility. These interactions could cause slight changes in Pluto's orbit over time, leading to minor variations in its path. However, given the long timescales involved, these changes are likely to be gradual rather than catastrophic. Despite its relatively small size and distance from the Sun, Pluto continues to offer valuable insights into the workings of our solar system. Its unique orbital characteristics, including its interaction with Neptune, highlight the complexity and interconnectedness of the forces that govern the motion of celestial bodies. The study of Pluto and its orbit has implications not only for understanding the dynamics of our solar system, but also for exploring the broad patterns of planetary motion that may exist throughout the universe. As we continue to study Pluto, we are reminded of the vastness and mystery of the universe. Even though Pluto may no longer be classified as a full-fledged planet, its place in our solar system remains a vital piece of the puzzle in understanding the evolution of planetary systems. By continuing to explore these far-flung regions of space, we can gain a deeper appreciation for the forces that shape the cosmos and our place within it. The ongoing study of Pluto and other Kuiper Belt objects promises to yield new discoveries that will continue to challenge and expand our understanding of the universe.